So we were trying to look for an example of this application of superposition principle. And so we have one object which is in gravity, and what is not shown on the figure is that it is fixed on the top end. Okay, it is fixed on the top end. So I have an object which is fixed on its top and gravity is active. So it is in gravity, and I have a load P which is acting on the opposite face on which it is fixed. How do I use the superposition principle? Excuse me. So I'm going to convert this into two boundary value problems. The schematics of the boundary value problems are already shown. Okay, so this is the second boundary value problem, and this is the first boundary value problem. Okay, let us see how I have already solved it using this superposition. The first boundary value problem, as you can see from the schematic, I have already split the original problem, which is this guy, into these two boundary value problems. So this is the first boundary value problem. I only have a body force and there is no traction on any of its surfaces, which is what is given here, and the displacement on the top boundary is 0. So there is body force. Traction is 0 on every face, and on the top surface, top face, the displacement is 0. Whereas for the second boundary value problem, this is what I have. I don't have a boundary, I don't have a body force. The displacement is 0 on the top anyway, which is prescribed again. Not anyway, it is prescribed. And there's a traction at z is equals to L. Okay, and there is no traction at z is equals to 0. So what are those alpha and betas? Can we write my given problem in terms of this? So in my given problem, what is the body force on the right hand side? Body force is minus g k hat. What am I using? Z hat? Take z hat. What is the displacement on the top? Is 0 at z is equals to 0. What is the traction? The traction is minus p. I'm using z hat at z is equals to L. Okay, so this term should not be there. At z is equals, otherwise it becomes an accelerating problem, right? And so this is what I have, and traction is 0 at all other boundaries, right? So let me see if B is alpha B1 plus beta B2 vectors. This is minus G is equals to alpha. This is the second boundary value we said. The only confusion is the way I have written. No, this is fine. No, there's no confusion. So this is B1 here. So B1 is minus G. So alpha times minus G. Everything in Z hat. Plus B2 is 0 anyway. So I have 0, which means alpha is 1. Likewise, let me look at displacements and tractions. So if I look at traction is alpha T1 plus beta T2. My overall traction is minus P. Of course, everything is in plus Z direction. This is alpha is 1, but my traction is 0 anyway. So this term is essentially 0 plus beta times the traction is minus P, which means beta is also equal to 1. Can I write the displacement boundary conditions using the same alpha and beta? If that is the case, then my superposition principle is complete. I'm not complete, I'm able to apply to it. So UO1 plus UO2 beta times UO2. Both UO1 and UO2 are 0. U is also 0 at the top. So this is 0 and this is fine. So I can clearly split this problem, the given problem, in terms of two boundary value problems. And as you will see, these problems are actually very easy to solve. instead of the moment body force comes in, remember when we were trying to do this Beltrami Michel conditions, even when we had body force, when we don't have body force, the right hand side has become 0, right? So the problem greatly gets simplified when you have to solve homogeneous partial differential equations rather than inhomogeneous partial differential equations. So superposition principle actually is of great help in solving many problems. Another such example is something which we will see next. Okay, this is the application which you saw, and this Clement's problem. We will solve this problem in a couple of weeks, but you should have an idea of what this is. It's a semi-infinite geometry. What is a semi-infinite geometry? Semi-infinite geometry is that geometry which you get when you cut an infinite object. Common example of semi-infinite object is the floor on which we all stand, the ground. Okay, what is infinite? Long enough, right? Long enough so that the every other variable of interest is dying except the position vector. And there is another problem called Bose-Nesque problem. What is the difference between these two problems? In the first problem, the geometry is semi-infinite. In the second problem, the geometry is also again semi-infinite. So the geometry is the same, right? In the first problem, it is a point, it is a line load. Imagine there is ground, and on the ground you have placed a heavy rope, and due to the rope, weight of the rope, you do get some stresses in the floor. That is what we analyze when we analyze a Clement's problem. You have a line load, and whereas in a Bose-Nesque problem, this is due to a distribution load. So once you know the solution of the Clement's problem, you can use this, use the superposition principle, and so basically I'm going to split this problem as a sum of semi-infinite load at this point plus semi-infinite load at the next point, and so on and so on. Simply, I will integrate the Clement's problem solution, and I'll get the solution of the Bose-Nesque problem. Okay, so superposition principle is very nice, looks simple but very powerful. It instead of solving more complicated equations, if you are able to split your problem into multiple smaller and smaller problems, you should be able to do it. And we are not restricted by whether it is in the previous two examples, we have split our given object into two different problems. If required, you can split into many more objects, not a problem. Just that these conditions should be there. Whatever scaling factors you use for the boundary conditions, same scaling factors should be applicable for the body forces as well. That is all there is to it. Okay, so we will, this is it for this lecture. So we have looked at the stress formulation. The stress formulation led us to Beltrami-Michel equations, whereas the displacement formulation has previously led you to Navier's equation. And there are two primary properties for this boundary value problems. First is the uniqueness, which was taught in part 1, and the second important property is the superposition principle. You have seen its, you have seen the theorem or the principle. The proof is straightforward, which I will leave it to you as an exercise. So I have not gone through the proof. As I told you, the focus of this second half of this course is on applications. Okay, enough mathematical foundation has been built, so certain things are left for you. So the proof is for you to look up or try to do it on your own. But I've given you the principle and some applications. Okay, so when you have a complicated problem, you don't have to solve. That doesn't imply your level of sophistication has increased. If you're smart, you should be able to split the problem into simpler and simpler boundary conditions, and with the geometry remaining the same. Okay, so we will start the next lectures with the planar problems. Thank you.